Welcome to this presentation in the series, Electronics, the Story of One Human Lifetime by David Beams and Gary James. I am David Beams. I am an Associate Professor Emeritus of Electrical Engineering at the University of Texas at Tyler. This presentation will be a little different from other presentations in the series. It will contain technical content, but it also contains what I think is a life lesson for practicing engineers. You know, you can be technically brilliant, but being smart is no guarantee of success. You have to be able to read the situation, and sometimes you have to know when to keep your brilliance to yourself. This is a story that goes back to the 1980s, but the lessons are timeless. The company for which I worked at that time produced a microwave Doppler ground speed sensor for off-road vehicle use. Its purpose was to provide a non-contact measurement of vehicle speed. This was useful in applications where wheel speed was not a reliable measure of ground speed. Agricultural and construction vehicles operating on soft ground where wheels could slip would be examples. So let's start with a few basics of Doppler velocimetry. Let's take a Doppler transceiver, that is a combination of a transmitter and receiver, and it's in motion with a velocity, v sub t, approaching a reflecting surface at 90 degrees, that is normal incidence. The transceiver mixes the transmitted signal, or the incident signal, with the reflected signal. This mixing produces an output signal whose frequency is equal to the Doppler shift frequency, which is designated as f sub d. According to my own analysis, the Doppler frequency f sub d is given by this relationship, where f sub m is the microwave frequency, v sub m is the speed of propagation of the microwaves, and v sub t is the transceiver's velocity, as we've noted before. Like I said, this was from my own analysis. But if we let v sub t in this expression be 0, this gives a Doppler frequency of 0, which it should. And if v sub m is much larger than v sub t, the Doppler frequency becomes simply this, which is a known result. So I think my derivation is correct, and in the following, we're going to work with this expression in any case. The sensor used a microwave frequency of 24.125 gigahertz, and v sub m was the speed of light, 2.998 times 10 to the 8th meters per second. This gives a Doppler frequency f sub d of 160.9 hertz per meter per second, or 71.9 hertz per mile per hour for normal incidence. But the vehicle moves parallel to the reflecting surface, that is the ground. So sensing this motion required mounting the sensor at some angle theta with respect to the vehicle frame. The component of vehicle velocity that's in the direction of the sensor now is v sub t multiplied by the cosine of mounting angle theta. So the Doppler frequency should be what we've seen before, multiplied by the cosine of theta. The design value of theta was 35 degrees, which gives a Doppler frequency of 131.8 hertz per meter per second, or 58.9 hertz per mile per hour. But someone, I heard that it was a German agricultural engineer, published a paper that stated that our radar velocity sensor read slightly low by a few percent without secondary calibration after installation. In other words, the default calibration constant seemed to be off somewhat. So the German says, yeah, it does seem like the Doppler radar has a bias error. But one of the 5 engineering managers, we called them the Gang of 5, said, ha, the German guy is totally full of Wiener Schnitzel. The equation is exact. Trust me, I know what I'm talking about. But some of us weren't so sure, including me. So I was having a conversation about this with Wesley, the chief designer of the sensor, and he said something about a spotlight effect. And in one of those rare epiphanies, I saw the explanation. An epiphany here is defined as a sudden manifestation or perception of the essential nature or meaning of something, when suddenly it all becomes clear. So imagine you're running a spotlight in a theater. You're up on a platform aiming a spotlight down on the action on the stage. The light from the spotlight is highly directional, and it's brightest right at the center of the beam. But looking down from your platform, the place on the stage where you see the brightest reflection is not where the center of the beam strikes the stage. The brightest reflection is actually at a point behind where the center of the beam strikes the stage. And the explanation is not all that complicated. So it's true that the light intensity of the beam decreases as we drop below the axis or center line of the spotlight, but as we drop below the center line of the beam, the distance from the reflecting spot to the observer is getting smaller, meaning that there's less path loss between the reflection and the observer. For a few degrees below the center line, the shortened distance has greater effect than the reduced light intensity. So let's look closer at the geometry. The sensor is mounted at a height h above ground. The physical mounting angle of the sensor is theta. The angle off the axis or center line of the beam we'll call phi, and r is the distance between the point at which a ray at an angle below the horizontal of theta plus phi touches the ground. So we can see that r is equal to h divided by the sine of theta plus phi. There is a well-known relationship that gives a received power in a radar system, which is this expression where P sub r is the received power, P sub t is the transmitted power, G is antenna gain, lambda is wavelength, sigma is the radar reflection cross-section, and r here is the distance to the target, in this case the brightest spot on the ground. For our purposes, we assume that everything except G and R will be constant, and G is a function of phi, and R is a function of theta and phi, as we've already seen. So for our purposes, we will write the reflected power as a function of theta and phi, and we'll take all of those constant terms and just roll them up into a constant we'll call beta. And then we'll normalize the return power as phi varies by dividing the return power as a function of theta and phi by the return power when phi equals 0. So the normalized return power is given by this expression. It's the gain of the antenna at angle phi squared divided by the gain along the center line squared, multiplied by, this is the distance from the observer to where the center line touches the ground, to the fourth power, and this is the actual distance from where the ray at theta and phi touches the ground, taken again to the fourth power. The idea is to calculate the normalized return power as a function of phi and look for the maximum. For this, we need measured data for the gain of the antenna, G of phi. I measured the antenna gain pattern myself in 1986, but I can't seem to find those data. But the internet knows all, and I found online information for a conical horn antenna that's similar to the one we were using. The following data show how gain in decibels varies with angle off the antenna centerline or off the antenna axis. dBi here, by the way, means gain in decibels over an isotropic antenna, that is one that radiates equally in all directions. Combining the measured antenna gain data with calculated distances gives the following normalized reflected power versus angle phi from the axis of the antenna. A clockwise rotation of phi is considered positive and represents an angle below the antenna axis. And you can see that the strongest reflection is found at about 3.2 degrees below the axis of the antenna. So the effective mounting angle of the antenna is greater than the physical mounting angle. With this particular antenna, the effective mounting angle would be 38.2 degrees. The bias error in the Doppler frequency would be about -4%. The German engineer found a bias error of about -3% in our sensor, whose antenna had a slightly higher gain and narrower beam width. So these calculations are not exact, but they are indicative of the kind of calculations that I did many years ago. I was thrilled with this simple investigation because I understood what was going on and I could explain it with numbers. Instead of keeping this to myself, or possibly just showing it to a couple of the other engineers, no, I decided to write a technical memo and have it distributed to the engineering department. This turned out to be a mistake. You remember the manager who said that the German engineer was full of Wiener Schnitzel? Well, by writing this memo, I unintentionally embarrassed him because my work and my memo told him and our colleagues, no, boss, you're the one full of Wiener Schnitzel. It did not go down well. You make me look foolish, will you? You'll pay for this. This episode only served to alienate us, and he regarded me after that as both a threat and a troublemaker. Had I thought through the consequences, I would have just shown my work to a few colleagues. I would have never written and distributed the memo. So my tale ends here, but just remember, being technically smart is necessary, but it's not enough for success. You have to be street smart as well. And if you remember only this one thing, this cautionary tale will have accomplished its purpose. A final word of advice as you travel your road to success. Be careful out there. Thank you for watching. We'll see you in the next presentation.